video got cut off, so I'm continuing on. So I guess this is going to be part 1.5 of the preliminary, or the first half of the preliminary Year 11 Engineering Studies electrical component. So this is done in Chapter 2. And where we left off is we were talking about how metallic bonds are crystals of metal ions surrounded by a swarm of electrons. We've covered that previously when we did materials in the previous chapter, so you should be familiar with that. If you're not, please put your hand up and let me know. I'm more than happy to go over it with people if I haven't explained it well enough in the first place. Okay, so the next thing we need to say is that electricity typically will not flow through covalent and ionic bonds. Now, there's a couple of exceptions here. So it's worth pointing out that water is a covalent bond, but water can conduct electricity. It can't conduct electricity on its own, but if you dissolve some salt ions in a tablespoon of salt, then it will, because that ionic bond, the salt, will dissolve. And when it dissolves, there's now free electrons which are able to conduct electricity. But typically, covalent and ionic bonds are typically not very good conductors of electricity. Metals, on the other hand, are good conductors of electricity, and they have lots of electrons which are able to conduct electricity. So electricity can be made in power plants or stored in batteries. We can imagine a battery as having one side that has too many electrons with negative charge and another side with too few electrons which has a positive charge. When we join these together with a circuit, with a conductor, a circuit is formed. The extra electrons from one side are able to flow to the other. Well, yeah, we'll stick with that for the moment. Eventually, the difference in the two charges will be equalized and you'll need to replace the battery. Now, we're going to draw a circuit. I'm going to find for you, we are not ready for Snoop yet. I am going to find for you some pictures of circuits. I had these ready somewhere, but you got to... Okay, so here's my circuits. When I was playing this out, I got a little bit off. Okay, so here I have a simple circuit. I have my power source, and I have a switch, and I have a globe, and it's just connected by presumably copper wire. When we draw that, we don't draw this diagram. It's a bit too hard to draw. We can once or twice for the sake of a demonstration, but we couldn't draw a complicated machinery like a refrigerator or a factory equipment using drawings like this. So instead we use, we've all agreed on some drawing conventions. So what we draw is we have the battery is drawn as a big line and a little line with a gap in between. Now the convention is that we draw the big side as positive. The idea, how I remember that, is that the big side takes twice as much ink. It takes twice as much ink to draw a positive sign, a plus sign, as it does to draw a negative sign. Now, what's interesting is that the current goes from the positive to the negative. Now, that seems like it's the exact opposite of what I just said, where we said that the electrons flow from the area with too much negative charge towards the positive charge. Well, current flows opposite the flow of electrons. Now, I first learnt that in this book, The Manga Guide to Electricity. Now, I would not recommend this for everyone, but it was okay. It's about a girl from the future or from some techno world, and she is failing her electricity exams, and because they're very difficult in the future. So to do a remedial course, she is forced to stay with this, I think he's a professor who teaches the basics of electricity, where she stays unsupervised except for this robot. I'll leave you to draw your own conclusions. Okay, so to start with, where after we go through the story aspect and we actually start learning things, she is concerned about these different units that she doesn't understand. What's the V? What's the A? What's the W? Well, we're going to learn about those things. I'm going to hold off. I may not even get to the W in this lesson, but I will get there eventually. So well, there you go. That's some of them. But let's get back to my notes here. And what we want to draw is a circuit with a battery and a globe and a switch. And we did just cover that. We just talked about this is what we want you to draw. And in this book, I learned that the current flows from the positive to the negative. The electrons flow opposite from the negative to the positive. But as far as we're concerned, everything flows from the positive to the negative. In a video, XKCD, it's Urgent Mission, I think it's called. XKCD is a comic for nerds. I think the guy worked for NASA, Randall, maybe I think his name was. Anyway, in this comic, you can see that a time traveler has gone back in time on an urgent mission to tell Benjamin Franklin, he's the guy on the American $100 bill, he flew a kite in a thunderstorm and was one of the first people to talk about electricity, that he is trying to tell him that, hey, it should be the other way around. It should flow from the, we should have it flowing from the, we should call the charge left on the glass by the silk should be the negative charge. XKCD is sometimes complicated enough that they actually have Wikipedia pages that explain the maths or science that's going on in the jokes. I like it, and I had got through about 1,000 of them before a friend of mine said, hey, you know, if you mouse over, there's a bonus joke. I did not know this, and I had to then go read them all again to see the bonus joke. So, yeah, you see, bonus joke. Yeah, the convention, it's a silly convention, but we just have to accept it. We don't have a time machine to go back and change that. So we're going back to the, we'll go back to my notes here. Okay, so the next thing we have to learn about is, well, what does the V stand for? Well, if we look at the HSC, we'll see that they don't call it V anymore. They've changed it. I've got this all the way forward. Okay, so if we have the HSC, what I've got here is I've got the 2019 paper. It's zoomed in a fair bit. I'll zoom it back out. And in the in every paper, they have a formula sheet. And the formula sheet has some things we should be familiar with and things that we're going to learn about later. But like we're going to learn about, so this P is for pressure, this P is for power, and down the bottom, this P is for power. We're going to learn about that in a second. We're probably not in this video, but we're going to get to there. Here we have this formula that says E equals IR, and you might be saying, what is E? I have no idea what E is. Well, in my notes here, I don't talk about E. I don't talk about E at all. So what I say here is, the potential difference between the charges on either side of the battery is known as the voltage of the battery. It's measured in volts. A standard battery has a potential difference of 1.5 volts. Well, and now we go to my mate Snoop. So Snoop, he has changed his name a couple of times. At one point, he tried to convince people that they should call him Snoop Lion, right? Normally, he goes by Snoop Doggy Dog, DJ Snoopadelic, a couple of names here, but I'm not going to stick with Snoop. I'm going to go with instead someone who uses the symbol E, and that's Eminem, right? But Eminem didn't always go by Eminem, right? So if you've seen this picture is from the film clip for Without Me. Unfortunately, I can't play Without Me because it has parental advisory. It's got the swears. But maybe if you ask your parents, you can listen to the song. And 20-year-old's rap song. Anyway, moving on. But yeah, so in this song, he says, nobody wants Marshall no more. They want Shady, I'm Chop Liver. Anyway, so the idea is that he's had different names. His name is Marshall, but then he went by Shady, Slim Shady, and all the other Shadys were just imitating. And then he went by Eminem. Well, the point is, voltage goes by multiple names. So what are the names that we give voltage? Well, let's go and have a look at, we don't need Shady anymore. If we go here, what do we got? I do need that, but I'm going to look at that later. Okay, so we've got volts, right? If I look up the SI unit volt, right, that's a thing. It's named after this guy, Alessandro Volta. And Alessandro Volta, so the volt is, let's say, it's the unit that measures electric potential difference, voltage, and electromotive force. So when we talk about that E, all these things, even though they all have different Wikipedia pages, they're all exactly the same. Well, okay, obviously they have different Wikipedia pages, they're not exactly the same, but effectively we're going to say, for our purposes, they're all the same thing. They're all measured in volts. Batteries have voltage or potential difference or electromotive force, right? So a lot of the time when people see EMF written on things, what they think it is electromagnetic force. And electromagnetic force is a thing. It's definitely something we talk about. But we are focusing on electromotive force. So I try to stress that motive every time I say it. And if we go to Copeland's book, let's start here. E stands for potential difference. Confusing, I know, right? But, you know, some people like Shady go by various names. Also known as voltage or electromotive force, sometimes written as capital EMF, sometimes written as low EMF. This is the measure of the pressure that is forcing electrons through a system. The name comes from the potential difference between the point where the electrons enter the system and where they exit it. It's measured in volts, and it can be likened to water through a pipe. So if we go to our thing here, they say the same thing, and we say, well, we compare the difference in water will run downhill relative to the difference from the top to the bottom. And the rate at which it flows, the rate per second, is the current. So that brings us to our next one. Current is written with an I. Why would current be written with an I? Crazy. Yet it is. Let's see if we can find that. So we've talked about volts, and we can close that now, I think. And we can now talk about the ampere, often called the amp. I have never heard anyone other than a physics teacher refer to this as amperes. It's named after Andre Marie Ampere, and the amp is the measure of electrical current, and electrical current has the symbol, if we just scroll down, I, which stands for intensité du courant, the intensity of the current, right? Why they couldn't just use C? The notation traveled from France to Great Britain, where it became standard, although at least one journal did not change from C to I until a long time. So yes, there were some people who said, hey, why don't we stick with C? But it wasn't to be, and we just have to accept that it's C. Now, to help you remember that, I do have, I mean, it's not a great rule, but to help you remember it is CIA. The symbol is, the word is current, the symbol is I, the unit is amp, measured, written as a capital A or ampere or amp. You don't include the abbreviation for, the accent graph for some reason on ampere. I tried, and then autocorrect said no, don't use it. Which is better though than what happened to Volta. Volta didn't get the A in his name at all. It's always just volts. I don't know why it's not voltas. Anyway, so voltage, also known as EMF, which it stands for electromotive force or potential difference, has the symbol of V or E. I know it's confusing, and the unit volts. Okay, the rate of flow of electrons is called the current, and it's measured in amps. The amount of current is equal to the voltage divided by the resistance. The resistance of an object is measured in ohms. So let's talk about ohms and Ohm's law. So we have Ohm's law is, so a guy called Greg, or I guess it's Gregor, like the guy in Sound of Music. Anyway, German physicist. Anyway, he came up with I, so we said that was current divided by voltage. So current equals voltage divided by resistance. But he had to measure resistance, so they gave it the unit, the ohm. Unfortunately, ohm, well, his name starts with an O. An O looks a lot like a 0, so instead they gave it the symbol omega. They do say that somewhere down here. But if we go down, so omega is this symbol here, or omega, as a lot of people would say. We can, rather than remember I equals V over R, most people remember it as V equals IR. Or, if you're the HSC, confusingly, E equals IR. Now, something that I didn't see until I became a teacher, and I thought, that's genius, I'm going to use that all the time, is you can remember as a triangle, if you cover up the letter V, well, voltage is equal to I times R. If you cover up the I, well, V equals if you cover up the I, you get current equals V divided by R. If you cover up the R, we get V divided by I. So you see how that works, right? If I go back to my notes here, I have that same diagram. The difference between my diagram and their diagram is that I use the symbols and they use the SI units. And I think there's a good reason to use SI units, because SI units don't use different letters like the way V and E are used. Now, to do that, we have to learn about power, and I keep talking about how power, it's coming around the corner. Just trust me, I've got my videos ready to go, but it won't be covered in this lesson, I don't think. And what we can look at here is that this is the one for power, and I've got my Abbott and Costello video ready to go. But what I have here is my triangle. So if you're looking for V, cover the V, and you get I times R. If you're looking for I, you get V divided by R. So hopefully that helps you. I try to write all of my three-letter formulas in that format because I find that helps people when they're learning their algebra. Okay, so we're ready to kick on. What do we do with this electricity that we've got? Well, let's have a look. Potentiometers are devices. I don't know why I go straight into here. I guess it works. Yeah, this is fine. We can go with this. Potentiometers are devices that can be used to adjust the resistance of a, yeah, that ties in nicely, resistance of the circuit. Also, we can use photoresistors, which are light-dependent resistors. We abbreviate that to LDR. We can draw these in a circuit that can be drawn as in different ways. So let me show you that. So I've got to jump a couple to get to that. Potentiometers. There we go. Okay, so potentiometers, they're dials or knobs. We use them for things like, can we use joysticks, but typically things like volume knobs. They can be used for all sorts of things. And basically, often a computer system or even electrical systems can detect that change in resistance, and that can be used to set multiple settings. The symbol for that is, well, depending how we want to draw a resistor, we can draw a resistor in two different ways. We can either draw it on the IEC standard, which is just to draw a rectangle, and often you write the resistance inside that rectangle, or as a zigzaggy line. And if we want to draw it as a variable resistor or a potentiometer, what we do is we draw an arrow joining into the side. And I'll just find an example that there shows a potentiometer. Okay, so LDRs are light-dependent resistors, and their voltage will change, or their resistance will change depending on the amount of light that hits them, and their symbol can look like that. And obviously, that rectangle can also be drawn as a zigzag. What we draw is the two arrows. The two arrows represent light hitting the resistor. So that's shown there. Another way, sometimes, I've only seen this once or twice in older textbooks, is it can be the Greek letter lambda, which, yeah, either you know or not, you can look it up. Not very common, so I wouldn't lose sleep over it. Okay, so what do we do with these things? I have covered that book. We're not going to get to semiconductors in this recording. That's going to be the next part. Okay, so we've got current, we've got potential difference, we've got resistance. Just in case I didn't read it, electricity is defined as the flow of electrons through a system. We've said that it can also be other things, but typically we're going to say flow of electrons through a system. And we remember that the current goes opposite to the direction of the flow of electrons, which it says somewhere in that manga guide to electricity. I just don't remember where. It's somewhere, but I just don't remember where. It might not be in the first chapter. Okay. So what do we got? The next thing we've got, well, we've got resistance. We've got this symbol here, rho. And now you might remember me talking about how we use the symbol rho to represent resistance. In this case, it's resistivity. So that every material has a different amount of resistance. And obviously, the longer the wire and the fatter the wire, the more, the bigger the cross-section of area of the wire, the more resistance it's going to have. So what are the different resistivities of materials? Well, the best conductor is silver. And silver has 6.3 somethings. The next is copper, and obviously we use copper a lot more than we use silver because silver is expensive. And even more expensive than silver is gold, which we generally don't use in electrical conducting very often. Copper, in some situations we want copper to be very, very close to being pure. So ETP, so electrolytic tough ETP, electrolytic tough pitch. Copper is pretty close to pure copper. It's more than 99%. And in some cases, we want even more pure than that. If that's the case, we if the impurities are silver, we don't count those because the silver it's better than copper, so it doesn't lose points for having little bits of silver. But often what we use is in like these big poles, transmission lines, is we'll use aluminium. And the reason we use aluminium is because aluminium, although it's half as conductive, it is a third of the weight and a third of the price. And that makes a big difference when we have to support the weight of kilometers of cable. When we have to support all the weight of those cables, it makes a big difference, and that we can have cheaper structures and cheaper lines, even though it's a little bit less efficient. So they do have a quote here from Thomas Edison, and we're going to talk about Thomas Edison and his mate, or his frenemy, Tesla, in a bit. Now, these two did not get along. And these days, the fact that the richest man in the world has a company named after Tesla probably has helped change a lot of minds in the public perception of Edison being a genius, and now that has shifted. Most people think that Tesla is way smarter than he really was, to the point where the New South Wales government is giving opinions on light bulbs. We'll talk about that in a second, and I will keep that open because I want to use that for another subject. We can close that. Okay, so Edison did a lot of things. Okay, so I'll just give the quote. I closed the quote. The quote was, "We will make electricity so cheap that only the rich will burn candles." And that has 100% come to pass. I used to play a game called Civilization 4, and then when Civilization 5 came out, I realized that I had a problem and that it was, negatively affecting my life, so I had to stop playing Civilization. And now I think we're up to Civilization 6, but, I've been free of Civilization since the early days of Civ 5. Though, despite my brother keeps asking me to play. Anyway, they have that quote, and I thought it's a good quote. And I often think about how great electricity is for what we get for it. That my mother, when I used to live at home, she used to complain about leaving the lights on and things. And I thought, if I had to pay $2 a day to keep the electricity running, it would still be an utter bargain. It would just be such a fantastic deal that what we get for our electricity is just fantastic. And this is no wonder that we have to worry about global warming, because it's just so cheap. It's so cheap, there's no incentive to worry. So what did Edison do? Well, Edison he built electrical power plants, and at the time, well, there wasn't really much to do with them. We have our poster here of Scranton Watt, the electric city. Now, I'm repeating myself because I just recorded an hour of audio, an hour of video that I'm moving my microphone, I apologize. And it didn't save, which was a bit sad. So if I'm repeating myself, I apologize. But in the office, it's set in Scranton, and they have this song, Scranton What? The Electric City. And they call it that because the electricity, well, okay, that's obvious. But why was Scranton the electric city? Well, Scranton was near Niagara Falls, and Niagara Falls was where Thomas Edison had his power plant. And his power plant, so we should talk about, so we're going to talk about in a second how we need to have moving objects to make electricity. Well, we don't need to, but the vast majority of electricity that we produce at the moment comes from generators. And how generators or dynamos work is that we turn something, and when we turn it, it makes electricity. Anyone who's seen the TV show Kimmy Schmidt, she has a crank when she was in the bunker, and she had to turn the crank, and she didn't know what the crank did, and it was likely that she was creating electricity. There's a bit of a spoiler, but I know what the crank does, but you'll have to watch to find out what the crank does. Anyway, so the point is that people had lights before electricity, but they had gas lights. And gas, well, it was dangerous. It could start fires. And when Edison started his power plant, Scranton was the first city to have electric lighting. So it got the name the Electric City. I also have this picture here from the song Electric Dreams, which was a movie that I saw when I was a little kid, and left a big impact on me. Okay, so Edison, what did he do with this electricity that he had? Well, he used it to make light bulbs, to make light bulbs work. So how did they make the light bulbs work? Well, the first thing, I'm going to go back a step, is that if you run electricity through iron doesn't conduct electricity very well. What it means is that it wastes electricity. It doesn't travel well through there. And what happens instead is it heats up. Now, generally, electricity, our cables heating up is a bad thing. But occasionally, we want the cable to heat up. In this case, we have this big, thick, not very conductive metal. And what we can do is we can let that poor conductor, that thing that has inefficiency, we can use that heat to boil the water in our kettle or to cook some 2-minute noodles on a saucepan. And this image was also used in the second hottest 100 cover. So it's so hot because it's red hot electrical coil, and it looks like headphones. Anyway, big album in my youth. I did have the track listing open. Yep, big Aussie hits, Silverchair, and another big hit for an Aussie. Green Day, pretty popular. This song, I don't know if they were Aussie, but Itchy and Scratchy, I like that song. Today, by Smashing Pumpkins, I really liked that song. Mazzy Star, I listen to that song about once a week because the YouTube on my school computer has identified that I like that song, and this one's not bad. Anyway, so Andre, bit funny. Anyway, so worth checking out if you want some 90s nostalgia. Okay, so we've talked about these circuits. We can close that. We do need that open. I'm going to keep that for later. Okay, so we've talked about how we can use electricity to heat things, but sometimes we want the opposite. We don't want heat. What we want instead is we want to produce the inefficiency. We want to come in a different form. We want it to come in the form of light. And in the case of light, well, we want to use a metal that doesn't heat up very much. We want a very thin filament that doesn't heat. So, or that doesn't melt is the key. So we use tungsten, which has the highest melting point of any metal. And we use a very thin filament. And when that happens, it's going to glow, and it's going to glow to produce light. Now, we don't use these incandescent light bulbs very much anymore because they're very inefficient. This uses 25 watts. And again, we keep talking about how we haven't talked about power yet, but watts the more watts, the fewer the watts, the better. So these days, you can get the same energy for a 100-watt bulb out of about 8 watts. So they're about LEDs are about 12 times as efficient, and they last pretty much forever. Whereas these incandescent light bulbs, well, if you shake them, they turn off. Or also, if you just turn the lights off and on too much, they're inefficient. So this is where I used to say to my mother when she'd complain that I had the lights on, that actually the thermal expansion of switching the light off and on actually does more damage. And these light bulbs, they're actually rated to the number of power cycles more than they're rated to the number of years. So when you consider the energy that's required to make a light bulb in terms of environment, in terms of cost, it was actually a lot cheaper, and it was better in all cases a lot of the time to leave the light on unless you were planning on switching it off in the next, say, 2 hours. So if you're going to be back and forth in the room, you're probably better off just leaving the light on. Anyway, I don't think that applies. It does apply for fluorescent lights, but it doesn't apply to. It sort of applies to fluorescent lights. It does not apply to LEDs. I would recommend you buy LEDs before. What do they call it? It's on the tip of my tongue. Anyway, before companies start making them less efficient and they don't last as long, because at the moment LEDs are pretty good. Okay, so we're going to close this light. Okay, so once we know that we can create light with globes, and we know that we can create heat. These days, very few people use electricity on the stove either. Most people You might use not directly like that. You might use an induction stove instead, or gas if you have it available. Sorry.
Induction fire.
Yeah, but I don't think the Uncle Roger, he didn't like the induction stove because you can't get good wok hay. Anyway, what we're going to look at is what do you do beyond that? Well, we're going to get to that. What we can do beyond light and heating is we can make things move. And that is a pretty important part, especially if you're making a company like Tesla's. You want to make things move. So Tesla, the car company, not Tesla, the dude. We're going to talk about Tesla again in a second. Okay, so we've talked about relative conductivity of materials. We've done that. We've talked about how silver has low resistivity, which means it's very good conductivity. 6 ohms per meter. I don't talk about conductivity very often, so I wouldn't worry about specifically how I phrase that unit. Okay, what we need to do is we need to be able to draw circuits. So here we have crossed wires and non-crossed wires. Now, I do not like drawing, maybe they've got their wires crossed out, but I do not like drawing crossed wires like that. I draw crossed wires like this. I like to have them like that. I like to draw it as a bump. To me, that's way easier to read. Wires that are joined should really be shown with a little circle around there just to mark it. Now, I will show that not everyone agrees with me. So in this case here, we can see that the dark circles show where the thing is connected, and we can see that these two wires are not connected. So just a difference. Now we can see these devices here. We've mentioned them in passing. We have resistors, obviously. We have diodes, and we have transistors. They can be drawn differently as well. So I don't know if presumably there were diodes and transistors in the previous one as well. No, there's Bunnings. So we can close that. We're not up to that yet. Oh, okay. So yeah, here we have diodes, and we have no transistors I can see. I mean, these might be transistors, but they're not clear. Okay. So we're going to go to these symbols. Okay. We talked about DC current is represented with a big line and a little line. Remembering the big line takes twice as much ink, just like a plus sign has twice as much ink. But we can also have alternating current. Now, I guess this is be where I talk about the war of the currents. Yeah, why not? Okay, so the war of the currents was between Edison and Tesla. And Edison, he started a company generating electricity first, and he hired Tesla. And he could see that Tesla, had some innovation or ingenuity, and he asked Tesla to work on his dynamos, a dynamo being something that generates electricity. And he offered Tesla $50,000, and we're talking in 1890s money, $50,000 if he could solve the problem. And Tesla presumably worked very long and hard to solve this problem. And when he did, he went to Edison, and Edison gave him a $10 pay increase. And I don't know. And he said to Tesla that you clearly don't understand American humor. And Tesla did not think this was as funny as Edison did, and he quit and he went and worked for Edison's competitor, Westinghouse. And then Westinghouse championed AC current versus DC current. Now, in the example that we talked about previously, we said that, there were movies about this with Benedict Cumberbatch, the guy from Sherlock and Doctor Strange, and the guy he played Edison, and the guy who played Tesla was Nicholas Hoult, who I know from About a Boy. I think of him as being the About a Boy guy, but he is also Beast in the X-Men movies. So anyway, we don't need that. We're done with that. Okay, so we're going to get to later. We're going to talk about the difference between AC and DC current, I promise. But in the meantime, the short version is that AC current was more efficient for a long time, and now it's been around for long enough that it's become the norm. That said, these days we could achieve things with DC. With modern computing, we could achieve things with DC, but you don't need to worry about that. Just forget about that. Instead, we're going to say AC, it's just more efficient. We just get more electricity for every kilo of coal that we burn if we use AC. So AC, it's better for the environment. It saves us money. We get more electricity. We get more good electrical stuff out of every kilo or every ton of coal. Okay, so we can close that. Okay, this is a thinker shield. It has both a potentiometer and a LDR, a light-dependent resistor, on there. So I just thought I'd point that out. POT for potentiometer, LDR. We use these. We have these in school. So if I haven't shown them to you, it's just an interesting application of simple electronics that we can program and do some interesting things with. We've talked about potentiometers. Okay, so now, finally, what do we do with this electricity aside from light and heat? Well, the big thing we can do, well, we have to make it first. Let's start there. We have to make it first. So how do we make it? Well, this is a Veritasium video, and in this video, Derek, or Dirk, if you watch, listen to Hello Internet, he's showing people a copper pipe. And first of all, he wants them to prove that copper is not magnetic, and he wants to check that there's no trick, that it really is a straight pipe. And then what he's going to do is he's going to run a magnet through this copper pipe. Now, he's proven that copper is not magnetic, and when he does that, we can see that the magnet, well, okay, so that's the regular thing. It goes through quickly, and then he's going to show these people, he's going to run the magnet through here. We can see that the magnet takes much longer to go through. And the reason it takes much longer to go through, well, the concept was developed by a guy called Michael Faraday, and he developed the first generator. And the generator is basically a coil and a magnet. And what he found is that movement plus magnets equal electricity. So what happens is that as the magnet moves through the coil, it produces an electrical field. And when it produces this electrical field, the electrical field that it produces, it eventually produces heat. And what that does is that there's less energy, there's less potential energy. So instead of falling at 9.8 meters per second squared, anyway, that's a reference to the Alicia Keys song that we talked about earlier in the year. And it falls a lot slower. What he's showing here is that movement plus the magnet equals electricity, and he's just using an LED. We're not going to cover any more of that. What we're going to talk about is that the reverse is, okay, so well, how do we make the movement? Well, we need to connect those magnets. In order to make electricity, we need to connect magnets to something. So what we connect those magnets to is we connect them to, well, initially water wheels. Now, people have used water wheels for a long time, the same way they'd used windmills. And a water mill was mainly used for grinding wheat into flour. So millers were usually rich people who would take what the farmers had grown and they'd turn it into flour that you could eat. And you could grind the flour by hand, right? It was a very time-consuming process. Or you could maybe get an ox and you could use a millstone. Anyone who's played Magic and heard of milling, that you can use a millstone to grind your wheat into flour. Or you could use a windmill or a water wheel, and that could also do the process without having to have an animal do work. You could just use the power of wind or the power of water. And so what Edison did is that he went to Niagara Falls and he set up a generator that worked off a waterfall, turned the water wheel, and that water wheel turned the magnets. So the rule we want to remember here is movement plus magnets equals electricity. That's the key. Now what's interesting is that the opposite is also true. So I guess this is where I use my Magneto line. And so when I was a kid, I used to watch X-Men, the X-Men cartoon, and Magneto would say, "Don't you know, Charles, that magnetism and electricity are related?" And the idea here is that movement plus magnets equal electricity. Okay, So let's have a look. Well, let's demonstrate that we can take a copper coil and a magnet and some electricity in the form of a battery, and if we give it just a bit of a push, just to get it started, well, they didn't even get a push. I find when I make these, you have to give it a bit of push. We can make these in class. I usually make these with year 10s. I haven't taught year 10s in like 5 years at this point, but this is what I often do with year 10 iSTEM or engineering classes. And it works a little bit better when you use the stuff they have in the science department. I think often year 11s make these if you do physics, but correct me if I'm wrong. Anyway, the point is that if you're going to make one of these at home, you follow the instructions. The important thing to remember is that this coil is actually coated in very thin clear plastic, and you have to scratch off plastic from one half of the side so that it can conduct. If you scratch the plastic off completely, it won't work. It'll get stuck, and let's find out why. Well, the first thing we need to look at is that magnets have these magnets travel in lines. Right, multiple lines. So this is the Earth magnetic pole. So we're just giving you that to start off with. And the concept here is that if we have electricity running through from positive to negative, so we have to use some letters, right? So we have 3 letters here. We're going to use the current, we use the letter I. That makes sense. That's familiar to us. And then this magnet, it's the worst looking magnet you've ever seen, but it's got north and south. And these lines are the same as those lines on the Earth's magnetic field. They're traveling from north to south, and we have multiple of them, the same way that there are multiple magnetic fields on the Earth. And we use the letter B for magnetism. I don't know why, we just do. We just have to accept that we use the letter B. And what that produces is a force. Now we can predict the force that's going to be. Now how do we do that? Well, we have 2 ways. This way here, both of them we call the right-hand rule, and this one here we're going to call the right-hand slap rule. So I kind of gave away the punchline here.
What did the 5 fingers say to the face? What? Slap!
Okay, so how does this rule work? Well, our fingers, the 4 fingers, look a lot like the magnetic field. 1, 2, 3, 4, right? So they look like the magnetic field. And our thumb represents the current, the flow of the current. So our fingers represent the direction from north to south. The thumb represents the current. And then the slap is the force, F. Now, if you can, that's one way of remembering. I will never test this, but it's very useful for people who are doing physics. You're going to learn this. The only problem with this rule is you have to put your pen, if you're right-handed, you have to put your pen down to use the rule to think about the diagram. So let's have a look at that. Well, there's another way of doing it. This way is the FBI rule and Fleming's right-hand rule. And so with this version of the rule, you make your hand look a bit like a gun. And counting from your thumb, so if you play piano, you'd go in the order of thumb, index, middle. So your thumb is the F for the force, the force of motion. B is the magnetic field, B, and that's on your index. And current is the middle finger. And when you point your finger, sort of makes a gun. And so people remember FBI the same way that it corresponds to the letters for the did they actually even mention the FBI, the Federal Bureau of Investigation? So it kind of pairs up nicely with our CIA mnemonic that we had earlier. We don't need that. Okay, so where are we up to? Yeah, here we go. The CIA mnemonic that we had earlier. Okay, so we're back to this generators. Okay, so we're closing that. Okay, so we've got this video, a DC motor. How does it work? Well, what's going to happen is we have the magnet traveling from north to south. So that's our fingers. And we put in a battery or a power source. And that power source is connected to our coil or our armature. And what's going to happen is that's going to rotate. Now we could, before the arrows come up, we can predict. So if we know the direction of the current, what I can do is I'm going to look at the arrow on the left-hand side here. the one near the north, and I'm going to put my hand out to my right, and I'm saying, well, okay, the thumb is going in the direction of that arrow, and my fingers, they're pointing in that same direction from north to south as the they're pointing in the same direction from north to south as that magnet, and because the palm of my hand is pointing down, that means that side of the armature, that side of the coil, is going to go downwards. So let's have a look. I mean, this is now the second time I've done this video, so I mean, anyway, it's going down. I was right. What's amazing though is what we're going to see that as it gets halfway, the arrow is suddenly going to change the direction for no good reason. And the reason that it changes direction is because there's a split in the ring. And you ready? Watching? It splits. Now, that's obviously more difficult than what we were doing with our homemade coil. So how we achieve that is by just removing the plastic coating from one side. What happens is that only half the coil is going to generate movement, and then the other half of the rotation is just going to rely on momentum to keep it going. So hopefully that makes sense. Okay. Now, we're getting pretty close to where I'm going to pause. After that, we're going to... Oh, okay. Yeah, that's my reminder that I need that video. Okay. So, what I'm going to talk about next... You can find DC motors in many... What I'm going to talk about next... Okay, so we're done with this page for the moment until we get to transistors and semiconductors. What we need is Copeland's page. Okay, so we have talked about these symbols here. We've covered diodes and transistors. Now, they don't have to be included in the circle. We've seen enough examples now to know that that's the case. I'll show you, I'll pause when we get to where we need this one to be. There we go. Okay. Even these examples here, we can see this transistor doesn't look like the transistor there. And we can see the resistor doesn't look like the resistor there. And we can see here we have diodes, and those diodes don't look exactly like the diodes there. The difference is really just a circles drawn around them, but it does confuse some people. So a diode looks like this. They can look like these, and we're gonna talk about that later when we get to semiconductors. So I'll leave that for the moment. And we're going to talk about series and shunt wound motors in the next one. What we're going to talk about is, okay, so you need to be familiar with all of these items. Capacitors. Okay, so I'll talk about capacitors briefly. When I was in high school, we'll say a student, for one reason or another, he said that he was, it may have been me, that he was impervious to pain. I don't know why the student thought that was a good thing to say. Anyway, a friend of mine, I don't recommend this. It could be illegal. Not in any way endorsing this, but he took the capacitor out of a camera flash, like a fancy camera flash, and he then hooked that up to a 9-volt battery and some. He used nails as the conductors, and used this to demonstrate whether or not the student was in fact impervious to pain. And like a yelp and 2 burn marks on the student's arm later, he was willing to concede that perhaps he was not in fact impervious to pain. So capacitors, what they do is they build up charge. Capacitor is a device capable of storing up electrical charge. However, unlike a battery, it does not produce the charge and it cannot hold it indefinitely. There's also electrolytic capacitors. You have the ability to read that yourself. Diodes allow only electricity to flow in one direction. A transistor acts as a switch or an amplifier. I'm stressing the amplifier because normally all we focus on is the switch. Now, just quickly to make that really apparent. We're going to go like here. No. There we go. Transistors can also, so that's a picture of a real, a pictorial image of a transistor. Transistors can be used as amplifiers in addition to being used as switches. We tend to think about their application in computers, which is to use them as switches. Loudspeakers work by a magnet, an electromagnet, and the electromagnet moves back and forth in the same frequency as the recording. It's the same, the opposite of a microphone. As a matter of fact, often you can use a microphone as a speaker and vice versa, especially an analog one. It's worth pointing out that Edison, in addition to potentially making the light bulb, which, as we mentioned earlier, the Australian government has an opinion as to whether or not he did invent the light bulb or if it was Joseph Swan. Not something I care enough about to weigh in on. And he also invented the first recording, the first audio recording, using the phonograph, using wax cylinders. And he also was a pioneer in video recordings. I think the French brothers, the Lumiere brothers, I know this because I went to a uni in France named after the Lumiere brothers, and they were the actual pioneers. But Hollywood set up to be as far away from Edison and his hired thugs as possible. Now, I could be slandering Edison, but that's I don't think he was as bad as people think, but I don't think he was the hero that previous generations thought he maybe was. And I think I'm getting pretty close to where I'm going to wrap up for today. We're going to talk about the difference between DC and AC motors in our next video. We're going to talk about semiconductors, and we're also going to talk about electrical safety. And I'll just check that that's what we're up to here. Yes. Okay, there's the difference between parallel and circuits in parallel and circuits in series. So that's pretty important. This is something you hopefully have done in, say, year 7 to 10 science. But the idea is that, generally speaking, everything we have is in parallel. I will probably talk about this a little bit later. But the idea is that if you have Christmas lights, if one light burns out, the whole thing is no good. Whereas if you have things in parallel, we can switch off an individual one, and it's also more efficient, as in we just get more energy out of circuits that are in parallel. We will definitely cover this later in, I say maybe, in the Year 12 course. I will make you have to calculate resistance. I'll show you what that looks like in the formula sheet. Whether or not I cover that at the end of term 4 remains to be seen. I usually like to cover it by term 4, by the end of year 11. But just in case I don't, I'll talk about here. So this is the difference in conductivity, and in the next video I will have something ready where I'll just show some quick examples where we do calculations and we compare series and parallel. I think that's where I'm going to leave it for today, and I will pick up on this recording tomorrow.